In today's lesson, we're going to solve problems by modeling systems of linear inequalities. So we're going to take everything we've learned up to this point and start doing some applications to it. So we've got a bit of a recipe here to solve, define the variables and set up all inequalities, graph all inequalities, determine a feasible solution region, determine if the solution is continuous, where we shade, or discrete, stipple. There's a note here. It says some solution sets may be restricted to specific quadrants. For example, most linear inequalities representing real-world problems situations have graphs that are restricted to the first quadrant. So what does that mean? When we look at our quadrants, they're labeled 1, 2, 3, and 4. So although axis and my y-axis is up there. So although when we're graphing a non-real world function, we could graph through any of these quadrants. When it's a real world situation, usually it only occurs in that very first quadrant. Okay? So what do we mean when we talk about continuous data? Continuous data is a connected set of numbers. In a continuous set, there's always another number between any two given numbers. Continuous variables represent things that can be measured, such as time. So for example, for time we can have hours, minutes, seconds. We can even have tenths of seconds. We can have hundredths of seconds. So there's all those points in between. Discrete data consisting of separate or distinct parts. Discrete variables represent things that can be counted, such as people in a room. So you don't have portions of people, you have whole number of people. So whenever you're counting objects, anything that you would count, such as your whole numbers, right? Anything that's counted in whole numbers would be considered discrete data. So let's see how this works in an example. So for example 1 here, it says solving a real-world problem by graphing a linear inequality with discrete whole number solution. A sports store has a net revenue of $100 on every pair of downhill skis sold and $120 on every snowboard sold. The manager's goal is to have a net revenue of more than $600 a day from the sales of these two items. What combinations of ski and snowboard sales will meet or exceed his daily sales goal? Choose two combinations that make sense and explain your choices. So if we look here, we need to start by defining our variables. So I start by saying let x equal the number of skis and y equal the number of snowboards. So I've defined those variables right away. So we're trying to figure out how many combinations of $100 in every pair of skis and $120 on every snowboard. Now we also know that x and y must be whole numbers. And the solution set is discrete. So what do we mean? Well, when you're counting the skis up, you're not counting 1, 1.5, 1.25. You're counting 0, 1, 2, 3, 4, 5, right? You're counting just those whole numbers, or even 2, 4, 6, 8. However you're counting sets of skis, and in this case it's a pair. So one pair would be counted as 1. So you start counting as 0, 1, 2, 3, and so on. You're not counting in between. You're not going forwards and backwards with your counting. You're just counting those whole numbers. Okay? So how do I set up this inequality? And how do I know that it's an inequality? Well, it says the manager's goal is to have a net revenue of more than $600 a day. Not equal to $600 a day, but more than $600 a day. So if I set up this inequality, I'd spend $100, not spend, but collect, revenue of $100 on every pair of skis, and I'd collect $120 on every snowboard. And the total, so summing those up, should be more than $600. So you can see that inequality right there. And every time you set up an inequality, it's going to be along the same lines, depending on how the question is worded. And that's the tricky part, right? So 100x plus 120y is greater than 600. Now, in order to graph this in my calculator, I need to rearrange and isolate y. So if I subtract 100x from both sides, I get 120y is greater than negative 100x plus 600. Divide through by 120. And we've got y is greater than minus 100 over 120x plus 600 over 120. Now, can I simplify these? Sure. Do I have to? No. Okay, there's no reason why you would have to do that. Using your graphing calculator, you're going to solve for your x-intercept and your y-intercept, and then we can graph this. So let's take out our graphing calculator and do that. Putting in my linear inequality, I'd put in negative 100 divided by 120x plus 600 divided by 120. Now, if you do what we've been doing before and hit zoom 6, you may or may not get the graph you're wanting. In this case, I'm glad that it's there, but because our numbers are starting to get bigger, and this only allows my graph to go from negative 10 to 10 in both the x and y direction, we won't always get our graph to show up nicely. In this case, it actually worked out really well. But you can see that all of the important information is occurring in quadrant 1. So although it graphs in all 4 quadrants, you may want to click on window here and adjust your window so that it represents that first quadrant a little bit better. So my x-min, I'm going to just go from negative 2 to 10, and in my y-min the same thing. And instead of hitting zoom 6, which would recenter it, I'm just going to hit graph or trace. And now I've got a better visual of what's going on in that first quadrant. Let's get my x and y-intercept. I'll start with my y-intercept. Put in x value of 0, and that gives me a y-intercept of 5. Then go back, second trace, and this time we're going to go find our x-intercept. Left bound. I'm trying to hold it down, it wasn't working, so I guess I have to click all the way. Right bound. Guess, and that gives me 6. Okay, so now we have our x-intercept and our y-intercept. We can graph in that quadrant. So this is my x-axis, my y-axis. I've got my y-intercept of 5, my x-intercept of 6. Now before I go ahead and graph this, I'm looking at my inequality here, and my inequality is showing me that I've got a greater than. Okay, so that means I'm going to be shading above, and my line is going to be a dashed line. So I can write that out somewhere here. It's a dashed line. So we'll put that in there using our straight edge. Okay, now I said shade above, wherein in fact, if this truly is whole numbers, shading implies that if I do this, that implies that all of the values above that line, up to that line, but not including that line, are possibilities for the number of skis and number of snowboards. And that's fine if I choose a value like this, for example, which might be 1 and 6. Okay, so that would be an x value of 1 and a y value of 6, meaning I would have one set of skis and 6 snowboards. But what if I pick, just erase that, oops, put that back, erase my axes. What if I chose a value that was a little bit over, and it would be 1.5 and 6? Well, I can't buy, well, I'm not going to want to sell 1.5 skis, right? That doesn't make sense in terms of my daily sales goals of what combinations, right? So the only values that are going to make sense are those whole numbers. And how do we indicate that on the graph? We call it stippling, which is just a whole bunch of dots. Okay, so dashed line and then stipple. Above. 2 P's there. So we're just going to be doing, right, instead of just shading, stippling, and that lets me, or whoever's looking at your work, know that it's only, those look like dashes, those should be dots. More like that. Okay, that all of those values are discrete. Okay? So it says choose 2 combinations that make sense and explain your choices. So looking at that stippled region, we could choose any 2 values, okay? Or any 2 combinations of values. So if I chose, for example, the order pair 7 and 4, right? An x value of 7, a y value of 4. That means I'm choosing 7 pairs of skis and 4 snowboards for my daily sales. And I want to see if that is going to actually make this inequality here true, right? That still has to hold true. Now you can plug it into your solved inequality down here, but I always like to go back to the original. So if I substitute in for 7 for x, and 120 times 4, is that going to give me a daily revenue of greater than $600? So it would be $700 on those skis and $480. And so you're testing, so you're not going to rearrange, you're just going to test. So that gives me $1,180. And yes, that is greater than 600. So that's one valid solution, right? That's one combination of sales that would give me what we're asking for. So I'd like you to choose another one. Okay, choose another one other than 7, 4. And then here's another one that I chose, was 2 and 10. So those are 2 that I know work. I'd like you to try another one on your own that you think would work for this and just test it out, okay? Just keep in mind that it says choose 2 combinations that make sense and explain your choices. So make sure that when you do choose your combination of skis and snowboards, that it's still valid for that situation. meaning greater than 600. Let's have a look at example 2. A company makes 2 types of boats on different assembly lines, aluminum fishing boats and fiberglass bow riders. When both assembly lines are running at full capacity, a maximum of 20 boats can be made in a day. The demand of fiberglass boats is greater than the demand for aluminum boats, so the company makes at least 5 more fiberglass boats than aluminum boats each day. What combinations of boats should the company make each day? Now, again, I'm going to start by defining my variables. I'm going to let x equal the number of aluminum boats. And y equal the number of fiberglass boats. Now, we know that x and y must be whole numbers. Why? Because I'm counting boats. And the solution set is discrete. Okay? Now, this should give us one inequality, and this should give us another inequality. Now, the first inequality here says when both assembly lines are running at full capacity, a maximum of 20 boats can be made in a day. So the total number of aluminum boats plus fiberglass boats should give us a maximum of 20 boats. So that means maximum less than or equal to. So that's what that means there. Now for my second inequality, it says the demand for fiberglass boats is greater than the demand for aluminum boats. So the company makes at least 5 more fiberglass boats. So what does that look like? At least. So I've got y, which is the number of fiberglass boats, is greater than or equal to x plus 5. Is that saying what we want it to say? The demand for fiberglass boats is greater than the demand, so that's what that's saying. Fiberglass boats is greater than the demand for aluminum boats, so they make 5 more fiberglass boats. Now initially this looks like, well, you added 5 more to the aluminum boats, but you take however many you made. Let's say you made 10 aluminum boats, 5 more. That means that you've got 15 fiberglass boats. So although we're adding the 5 to the aluminum boats, the total there is the number of fiberglass boats being made. And that's where I find students get the most confused. So inequality 2 is already isolated for y. Let's rearrange this one. Not much to do to get there. So negative x plus 20. And I'm going to take my graphing calculator and put those in. Okay? Got previous example here, so let's take that out. Negative x plus 20 for the first one, and x plus 5 for the other one. And we can zoom 6 if you want. Now I can only see one of them, so let's change our window. And if I change it back to where I was, let's use negative 2 just so we can see. And hit trace. That makes things a little bit better, but I still can't see the other one. So how do I know how big to make this, right? Well, if, oh, that's why. 20, not 2. Let's change that in there. Oh, I put that in there. if that's a 20 here, that means my y-intercept is 20. So my y-intercept is 20. My x-max is only at 10. So what if I made that at 25? My y-max, sorry. Well, now I could see that better, and the other one. So they're both more visible. So when you're switching your window around, you're going to see what makes sense for the situation. And because we know that y equals mx plus b, this is what I was looking for. It would have been an easy way to make sure that my y-intercept actually lands on that graph. And I identified the 20 there. I could look at the other one, but this one here wasn't as important because it's 5. That was easier to see already. Okay, so now that I have that, we can find our x-intercept and y-intercept for each of them. I'm not going to take the time to go through that again. You guys know how to do that. So my x-intercept for the first equation is 20. And my y-intercept is also 20. For the second inequality, my x-intercept, there is none. That's visible on the graph. And my y-intercept is 5. So when I'm graphing this, okay, these are both solid. Lines, and because it's discrete data, I'm going to stipple. For 1, I'm going to stipple below, and for 2, I'm going to stipple above. Okay, so draw those lines on here. This one here. And this one here. So this is 20 and 20, and this here is 5. So if I'm going to stipple below, this is my second equation, this is my first equation. If I'm going to stipple below the first one, that would be everywhere here. Right? And if I'm going to stipple above my second one, you can see my stippling is going to overlap in there. So I can erase all these ones. Try not to erase my lines. Okay, like that one. Put that back. Now the only thing left to do is to find this point of intersection using our graphing calculator. Reminder, second, trace 5, enter, enter, enter. And you could see it's at 7.5 and 12.5. And make sure you label that on your graph. So it says, what combinations of boats should the company make each day? And any point with a whole number solution in that stipple region is an acceptable combination. So if I chose, it's hard to choose, but you can see here, if this is an x value of 7.5, right, it's going to be less than that, right? And you've got a y value here of 5 and a y value here of 20. So I can choose values such as 3, 12, right, which that would be 3 aluminum and 12 fiberglass. And what I would have to do is check that into both inequalities. Okay, so y is less than or equal to negative x plus 20. If I put that in there, 12 less than or equal to negative 3 plus 20. That would give me a 17 here. Is 12 less than 17? Yes, it is. If I try on the other one, y is greater than or equal to x plus 5. Y is 12. X is 3. So 12 is greater than or equal to 8. Yes, that is. So it's valid in both of them. So that would be one possible solution. So in this case, what I have here is 3 plus 12, or 15 boats total, with 9 more fiberglass than aluminum. Okay? Now we have one more example here, but I'm actually not going to go through it. I can fill out the solution for you. I don't love this example. It's not really easy to figure out what they're asking about. The nice thing about this example, it is continuous, but the only difference between this one and the one we've been doing really is that you're going to be shading instead of stippling. But the example, it's a little bit hard to understand because we don't all have experiences with sailboats and understand what's happening with this. But I will fill out the solution so you can go ahead and check that out in our notes package. We'll do more examples in class that are a little bit easier to understand. Thanks for joining me today.